We just discussed about climate and quantum for climate. Sayon, your topic is not far away from that. Welcome. Welcome to the WOMANIUM Global Quantum Program. Very happy to have you as a speaker. Sayonsom Chanda is a senior scientist at the National Renewable Energy Laboratory in Boulder, Colorado in the US, working in between advanced computing technologies and the electric power grid. And he is not only a scientist, having worked at NREL now, previously Idaho National Lab, also at the National Grid, but he is also a founder. He founded 2 tech startups and also helped them raise venture capital and develop commercial solutions for the utility industry. Not only that, he is also a TEDx speaker on AI applications in the energy industry, is an author. He wrote the book Resiliency of Electricity Distribution Systems, and he wrote numerous papers and holds 3 patents in cloud computing for power systems. Sayon, really great having you.
Perfect.
Please take it away, Sayon. Very excited for your talk about quantum computing for power and energy systems.
Oh, well, thank you. I hope that I meet at least the least of your expectations. I will be speaking to you all. I mean, most of you may have like deeper quantum computing backgrounds than myself. So I look forward to learn as much as I speak by engaging with you. But I have been working a little bit on the side of bringing to industrial applications some of the quantum computing technologies that other pioneers like you and maybe the previous speaker and others have been working on to the power and energy systems domain. So go to the next slide. So as a part of my work, both as a scientist at NREL or as an engineer at a utility or as entrepreneur, I have asked on a few like formal surveys and on informal, like conversations in a conference breakfast table about their thoughts on energy. And most of the times when it comes to the word energy, people recollect their bad experiences, like when they lost power or the wildfires in that knocked down power for like 3 days or something. But I kind of insisted that, okay, that has been the past, but going forward, what are some of your positive expectations about energy? Now that kind of, and when I think back or reflect on those conversations, you can clearly see that energy is not something that in itself, it's very different from the pharma industry in the sense that it kind of connects 3 aspects in one frame. It touches our own lives, it touches our communities, and it touches our and the entire environment at one go. So when I segment some of those thoughts that people have about energy, they mention they want their energy to be reliable, cheap, want it available 24/7. They recollect things like smart appliances, like everything talking to one another. They want their electricity bills to go down through energy efficiency. They want convenience. And then there's some people who speak about energy in their communities, and when they talk in that frame of mind, they speak that energy should be resilient, that even after a storm or a wildfire, people don't lose power. They talk about things like energy security, energy justice. And then when people talk about energy in the environment, then people talk about like net zero, like not adding to climate burden. Now, why I'm kind of speaking about this and I'll connect it to quantum is that for the most part, all these things are the wants or the goals that we would want to have in our society, while a lot of it is missing. And why is it missing is where the quantum piece would fit in. So we have these positive aspirations about energy, most of which are met like 99% of the times. But there is those 1% of the times when there is a wildfire or an extreme event that causes significant problems in our society. Now, with that said, I'll share some of my experiences of how computation is typically done in the utilities, and if there is a need for different kind of solutions in like quantum-based solutions or not for the energy industry. So now the utility industry has been there for about 150 years, and computation has been used in the utility industry for about 80 years as of now. It started nearly in the 1940s and 50s when some very super early versions of computers were used to define the load flow problem. And then they were used for understanding how the voltages across the different circuit networks would be used for. And that was done in 1950 using the early UNIVACs. And since then, it has been the core or the very DNA of how the entire power grid is run. Like every day, millions of power flow solutions are solved across the world. And then there are several categories of problems that get solved. One of them is a unit commitment problem, is where a unit commitment problem, if you're not familiar with it, is that identifying which generator can be used to feed a load. And then these are like some of the operational problems. But then there is the other category of problems that is solved in the utility industry, which is about planning for the future grid. Like when we want to make the future grid into whatever those reliable, resilient, net zero, people do some activities, the planning activities, and those are done through Monte Carlo simulations or contemplating a significant number of possible cases, running those cases with different initial conditions and understanding what would be the best use of our infrastructure or what elements we need to add in our infrastructure to make it possible. And the other thing that people do is do some sort of probabilistic forecasting or understanding how much load demand is going to be. And these kind of activities generate terabytes upon terabytes of data daily. And these are just some of my own experiences. So when I was doing Monte Carlo simulations as a consultant, we were dealing with about 3,000 transmission nodes generating 25 terabytes of data daily. And we were racking up tens of thousands of dollars in Amazon bills every single day for generating the solutions. And similarly, when I was doing load forecasting work for the utility, and these processes are extremely slow. Some of the processes run for 10 to 12 days, and some of the Monte Carlo simulations can take up to like nearly a week just to run. But on the other hand, for more operational purposes like unit commitment and power flow, they ran simulations for up to like 50,000 buses, and the computation has advanced enough where they can have good enough solutions in a few minutes. So now the reason I speak to you about this is because in the power sector, there will be a classification of problems where people need to decide whether quantum computing is actually required for solving those problems or not. Because billions of dollars have already been invested on the power flow problem or the unit commitment problem. And unless something that is orders of magnitude better than what exists today, the quantum computing will not be required to solve those kind of things. But then on the top two rows of my slide, I'm saying that these are cases where quantum-based solutions can come in handy. So this is one perspective I wanted to share as people are thinking of more of reliable, resilient, and climate-friendly energy grid. Now, that being said, there will be a classification of problems where quantum will be required and some where quantum will not be required. But then I also wanted to highlight in this my presentation that there are some unsolved problems in the power grid that planners do not either consider or they think it's too complicated to even consider. So they make it a part of their assumptions. One of the things is that as everything literally becomes an Internet of Things device, like an IoT connected device, the the problem space, the number of variables that can be part of a control plane is exploding. Like every dishwasher is a smart dishwasher and probably has a role to play in the power grid, right? Through, when you are doing, say, time of use, pricing and whatnot. The number of scenarios that people plan for is very limited, but with more wildfires or, carbon neutrality goals or whatever might be the scenario that people plan for are limited and it needs to be expanded. So not all scenarios are considered as of now today. So that's a problem that we overlook. We say that, oh, let's assume this is going to happen. The other thing is that as the power grid is evolving, one thing that you might have heard of is the concept of microgrids, where a small section of the grid can isolate from the main grid and still continue to be functional. So the government is encouraging more microgrids to increase the resiliency of the power grid so that a wildfire in Southern California doesn't affect homes in Northern California, things like that, or wildfire in say Canada is not responsible for some of, say, the power related shutdowns in Albany area, as it happened a couple of months ago. So those kind of partitioning problems are not solved by the traditional computing software that the industry has already spent billions of dollars in. So these three are the top contenders where quantum-based solutions can start coming in. And then there are some solutions which are a little bit out there, the last two I mentioned, which is, the power grid is always at risk of cyber attacks. I mean, the power grid is attacked by people with malicious intents through cyber methods almost thousands of times daily. However, most of the cybersecurity researchers today do not have something called a gain of function research, where they cannot emulate, okay, if this, say, malware gets more and more potent while remaining invisible for the first couple of attacks, and this attack is starting from someone's thermostat, for example, how would that entire power grid be taken down? So those kind of speculations are not very scientific at this point, and that is because it is not possible to model or run those very fast simulation for as many number of scenarios using today's traditional methods. So these are some problems that is going to have a big impact in the future, and where traditional computing solutions for the power system does not exist, but theoretically quantum might have some solutions. Now, these are some of the problems that I mentioned, but I also wanted to mention that, and as Nicholas was mentioning towards the end of his talk, where I just last heard him, is what are things that is possible today and what can be done in the future. And I really like this comment that honesty will really help frame the problems a lot better. So, the 5 problems that I mentioned in my previous slide are not done today, which I show on the left half of my screen. But then there are other categories of problems like unit commitment, which are power flows, where there are great classical computing based solutions existing in the industry, and there is no need for a newer kind of a computation, because a few milliseconds worth of efficiency is not enough for the industry to offset its tens of years of billions of dollars of investment, right? So if there are, and there is a lot of scientific papers, people from graduate schools publishing power flows on quantum computers, that's probably, just an academic exercise and not very likely to get industrial acclaim in the near term. But of course, now I believe that there are 2 things where people working on this combination of quantum and power system have an opportunity to work together on. One, which is going to be outright valuable, like mentioned, grid partitioning. When people are doing, say, transmission planning with lots of microgrids, how to island that microgrids in such a way that the overall resilience of the transmission grid increases, right? That problem has an outright valuable solution. It's an optimization problem, QAOA problem, that is not very well handled by classical computers, and they don't even try. A perfect use case for quantum computing, people working in the energy sector. And the second thing that what people can work on today is whatever can be easily validated, which is some large scale optimization problems where you have some classical solutions, but you see their convergence taking a lot of time. Can we frame it in such a way where using maybe a couple hundred qubits, which is available today, can you find better solutions? So if you start validating those problems today, and as more and more qubits start becoming available, you can scale up those problems easily. So people have to understand this distinction between what is going to be outright valuable and what can be easily validated, and start framing the solutions. And it is my personal belief that if we work on these kind of problems, we will be able to show greater value of quantum computing in the energy system than by trying to reinvent the wheel using another technology. So I strongly encourage uh, and motivate myself to um, design algorithms or try to understand what can be outright valuable, such as the grid partitioning problem. Now, whenever I speak at computing conferences or my peers and colleagues in this industry, many of them seem to have forgotten one very simple thing, and which is the foundation of what is the difference between classical computing and quantum computing. I mean, you see, computers emerged in the 1880s, right? When Charles Babbage was trying to do a simple math problem of finding the difference between two large numbers. And all he invented was a bunch of mechanical switches, electric switches that drove the mechanical relays, which could help him subtract numbers. So the key is here, electrical switches. And everyone seemed to like that idea of electrical switches. And over the next 150 years, say from Mr. Babbage's time till today, we have either improved or reinvented different kinds of switches, or have become very efficient in compacting the switches in like microchips, etc., etc. So our classical computing is all about how we can make better switches or pack more switches in the same space, Moore's law, etc., etc. But quantum computing, as you might all know, is a totally different paradigm. We're no longer trying to pack in as many switches or in the same space. So we have to be aware of that fact and understand that the problems that are solved through switching will be fundamentally and philosophically different from the problem that has to be solved when a completely different physics is being used. So I'll quote Mr. Feynman again when he says that nature isn't classical, goddammit. And because the problems that we are trying to simulate with quantum computers, say understanding customers' behavior, how they use energy, or try to simulate an infinite number of scenarios, or try to understand how cyber vulnerability or malware is going to evolve as it spreads across the network. These are something that switch-based algorithms or switch-based mindset of designing the algorithms will have very limited returns on investment. So it is very important for the power systems or the energy systems algorithm designers to understand that there is going to be a difference in how algorithms are going to be designed in the future. And that would probably start at the high school level, where you introduce people to different forms of algebra, and then start building the entire workforce based on that. Now, that I was speaking in the first half based on power sector, the power industry, or aspects of quantum computing. But as you might know, the energy sector, like how the entire energy gets, like produced, and that has different quantum computing applications of its own, especially quantum chemistry, which has some more realistic near-term benefits. So converting methane to methanol is an actively worked upon problem. And once done, it will have tremendous use cases in curtailing big issues like climate change and reducing global emissions, right? And the other thing that the industry is working on is designing of new materials. Now, many people have this perception that going all electric in terms of cars and feeding them through renewable energy like solar is the panacea that the climate crisis needs. But we have to understand that these electric vehicles are made of batteries, which are sourcing their batteries from a very finite source of lithium in very limited parts of the world. So we have to design and develop new materials that would make it truly a synthetic, renewable, regenerative process on how we can keep producing our next generations of transport. And those are some solutions that is not possible in today's, say, generative AI, or say, for example, an equivalent of ChatGPT and say that create me a new material for a battery, and you'll probably get some hallucinated answers, right? But quantum computing holds promise for that, and that is where some of the relevant use cases is going to show up. Now, of course, like as you design for energy storage, there is some scientific papers where people are solving Navier-Stokes equations or understanding molecular vibrations and their calculations using quantum computers. And that is a very encouraging aspect on how we can start understanding what the future needs from the power sector standpoint, where you start understanding how the grid is going to evolve, what consumer demands are, and based on consumer demands, you can design the energy sources using new materials, solving previously unsolved equations. So that, and both of these are only possible if we can streamline the power of a quantum computing resources and talents in the right way, instead of them having to reinvent or they spending their graduate school solving a power flow or a unit commitment problem on a quantum computer, which the industry will not care for because better classical solutions already exist. But there are problems where these kind of solutions are required, and people should focus on that. Now, the other aspect where I'm excited about personally in terms of quantum computing is quantum sensing. If you are not from a power systems or energy systems background, you may or may not have heard of something called phasor measurement units. It's a very important instrument in the electric power grid. One aspect that it's common knowledge that the entire power grid has a common heartbeat. It is like one machine that spans the entire United States and parts of Canada, and it is beating at the same frequency 60 times a second, 60 hertz. Any one of these devices fall out of step and it can bring the entire power grid down. And this happens time to time in the form of blackouts. Now, the way to keep all these billions of devices in synchronicity is through these devices called phasor measurement units. And they require one common source of time to make sure that everything beats at the same time. But as you see with more climate-related risks like sudden heat waves, sudden ice storms in unexpected places, the outages or the blackouts are going up and up. So we need to step up our game when we do better geolocation, time sensing, faster response to such kind of outages so that we can contain them. So here the developments of quantum sensing is extremely required. And I believe that within the next decade, the next generation of phasor measurement units will have some elements of quantum sensing. And that is a good area of research for people to work on. And that is very realistic in my understanding. Second thing is, and the other area of research that I'd quickly highlight is the quantum secure power grids. And NIST is helping my organization, NREL, and several others around the country in identifying quantum resistant algorithms for use cases such as the electric vehicle charging stations and how they map to the electric power grid, right? So electric vehicle charging stations are that one element in our society as of now, where two extremely important networks, the power grid network and the financial sector, come together at the same point of, like commonly coupled. So a vulnerability starting from an EV can take down both the power grid and can also walk its way across the financial transactions network, and it can really cripple a lot of things. We do not know how those things might go wrong. So securing those kind of transactions is also a near-term objective that people might might be worth considering for some people. So there are still challenges, of course, like this is not an off-the-shelf solution, but my focus is trying to bring attention to some of the more relevant problems that people should be focusing on and bringing these solutions to life. Now, I'm close towards the end of my talk, but I believe that this is a good time for all of us to build our quantum knowledge stack. Some of the solutions, some of the solutions are not, be realized or adopted by the industry tomorrow. But if we keep working on the right problems with the right focus and at the right intensity, we will be able to keep up with the increasing complexity of our times. Now, my observations is that, and I have tried to put it on a chart like this, basically is that you see a lot of hype around quantum computing, and there are many schools who would just do like a side project on quantum computing or something, where which is basically like copy pasting Qiskit code from somewhere and getting a result. That is good for getting a flavor, but that is just building onto the hype and leading people to more and more of a disappointment that, oh, this doesn't work, what do I do with it? Or throwing them into the deep end without giving them a deeper understanding. But I believe that in our community, we should, while evangelizing the power of quantum computing, we should also reinforce a couple of other things, like increasing academic focus on linear algebra. And at the same time, also keep explaining to people is that quantum computing is not going to see the meteoric rise that data science did as a result of Python and pandas and NumPy, right? So for quantum computing, or people who want to be quantum computing scientists, they also have to have a deeper understanding of the hardware that they will be working on. So people have to understand that this is going to be a lot more hard work than becoming a data scientist. And then based on that knowledge, they have to deconstruct some of the classical algorithms and try to build their own for their own specific solutions. So everyone's roadmap is going to be different, but by doing more of the hard work, high value work, we will be able to contain the hype and keep the communities focused on problems that really, really matter. So that's what basically I wanted to share as a part of my conversation with you today. And I'd like to, pause here if you have anything to add or chat about.
Amazing. Thank you, Sayon, for this really inspiring talk. This was great. From 100 years of improving switches to a totally new paradigm now, and how it can be applied and in which cases. People are really enthusiastic about your talk. Many compliments that I will share with you later. Thank you very much. I will share some of the questions, and everyone looking at this roadmap, right? You have all been covering a lot this month. So this is really good. One question from, let me go down, from Priyal from India is, gain of functions research on cyber vulnerability, which was early in your talk. Could you elaborate a bit more on that?
Right. Yeah, it's, gain of function is basically a term most biologists would use when trying to understand how a virus can become extremely dangerous. But similar research is done in similar research for doing cyber vulnerabilities is not very common. We can understand that, a malware can pass from one USB drive to another USB drive and 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 basically do the same thing, like stealing data or something. But it is possible to design malware which keeps increasing its potency as it moves from device to device. Now, that requires a lot of imagination and scenario planning, and it's extremely hard to simulate that using classical cybersecurity tools. So gain of function, if you look up the microbiology equivalent of it, it's about understanding how viruses in nature increase their potency or how they mutate over time. And then you'll be able to understand, and then you'll be able to map basically on how quantum computing can help mimic those natural evolutions in terms of man-made cybersecurity vulnerabilities.
Excellent. Then I will ask one more question, and then Vardan will also add more questions. Pablo from Argentina asks, it's really good and great that you highlight the history. Do we have a quantum Shannon theory well established?
That's a great question. I think the whole community should jump into that question. But Shannon's theory is universal in the sense that, but of course, there needs to be a better communication of that information theory, or how coding or encoding is to be done for qubits for quantum mechanical systems such as quantum computers. But I don't believe there is like a one-on-one mapping of Shannon's information or entropy for quantum computers. But I don't know, Marlou, I mean, you're more of an expert on this, if you want to comment on that as well.
Yeah.
Great. So, yeah, a couple of questions on this call, which I would like to feed are that you mentioned that some use cases are better than others for using quantum algorithms, and while doing so, you also need to make sure that these are actually run on the current NISQ devices. So I would actually ask you, what is the strategy about that? How you decide which use cases are better? And when you do decide that, how do you go about using those algorithms for the current error-prone devices?
Right, and that's a great question. I personally think that this is the point where we should start talking with the industry partners about what problems that they kind of are not solving, or even considering solving using their classical computers, or where their maximum costs are. So when we speak to electric utilities or OEMs such as General Electric, they mention certain use cases like one example, say this grid partitioning, for example. They said that, that is too difficult to simulate. We don't even consider that. And we just have experts who have worked in this industry for like 40 years and we just trust their brain. So that is kind of a good signal for us that, okay, that might be a problem where it is worth looking at. But then at the same time, from our team of experts in our organization or talking to industry folks, we see that if we do solve unit commitment, or basically the problem of which generator is supposed to feed the power, the utility already has an excellent solution for that using classical computers, and with more and more AI also, they have made billions of dollars of investment. So solving that problem on a quantum computer with noisy results is not going to impress them. It might even discourage them. So we definitely ignore that problem. But then problems where they have traditionally used like extreme human expertise to make decisions, or problems where the number of variables are too large for them to even model. For example, some of these climate related problems, say if there's a heat wave, how the load forecast is going to be suddenly improved or adjusted. Now, heat wave is a very complex phenomena which has multiple moving parts. It will increase people's increase demand for air conditioners. It is going to increase the, it is going to modify the physical properties of the conductors. It is going to make the transformers in the power grid heated up more, which might be, like more likely to fail. So a lot of interconnected models might start, like have cascade one after another. And those sort of scenario planning is not done in today's planning. So then we do adjust, say, a load forecast upon a heat wave by a certain factor. And that factor is, like smokes and mirrors. Someone from experience would say that, oh, if the temperature increases by 0.5 degrees Fahrenheit, let's adjust everything by a certain value, alpha. Now, how that alpha came, those are empirical results or someone's experiential results. But can we use an optimization problem that can handle a lot more variables in a reasonably good enough time to determine that alpha within, of course, like probabilistic bounds? That's a problem worth solving. And that is, I believe, going to have some value. And those are the problems that we would want to solve using a quantum computer in the NISQ era, where, we have proven QAOA, proven QBO. There are different VQE algorithms out there. So I think those are the problems we'd want to throw at the quantum computer.
Then regarding quantum sensing, you mentioned the energy grid, really important to have one synchronized time. Atomic clocks will be really important for that. Portable atomic clocks that are now being, the process is being upscaled for that to deploy those really widely. Where do you see more applications of quantum sensors in the energy space, and also what type of quantum sensors?
I mean, for the energy space, I believe the most near term is going to be more reliable geolocation, like quantum-based pressure measurement units, because that is keeping the grid stable is equivalent to our cardiac system being functional. But anything on top of that, whether you're trying to understand or coordinate electric vehicle charging and making sure that the charging apparatus or the transformers in that network are performing at their optimal best, that I believe is going to be a second layer of application. But once people figure out how to use quantum sensor to minimize blackouts through better geolocation or more precision in keeping time across these complex devices, I think that is a good area of research, and people should, and I believe it has a more near-term application than anything else at this point.
Both are indeed perfectly possible with quantum sensors, or will be. Another question was, fun and good question, which programming language do you use? Because Python is really common, but also extremely energy draining.
That's right. So this is actually a great question, because one of the things that I often, I met some university students, and we had a long conversation about whether he should learn Cirq or Qiskit or Q#. And at the end of the conversation, I was trying to convince him that it doesn't matter, because don't get stuck on the framework, just because as of now, if you really need to be like proficient in this era where you'd be looking for like quantum computing jobs or something, you have to know the hardware a lot more than the software, because at the end of the day, almost all these software is getting the backend compiled into some C code. And I personally have not written C code in the last 10 years because Python is just so easy to remember, even if it's computationally draining, right? So I personally suggest that the Microsoft of quantum computing is probably a decade away. Someone will eventually build it. But as professionals ourselves, we are still in that assembly language era of the 1960s and 70s, where we have to have a good understanding of both the hardware and the software. So for programming, I personally would still continue using IBM's Qiskit, and that eventually gets transpiled into OpenChasm, and that makes it quite portable, whether you are using, say, an IBM machine or some other vendor. Everyone would have some sort of support for OpenChasm. But on the other hand, if your domain is quantum machine learning, I would strongly encourage you to explore the Circu and the TensorFlow integration for Circu, because the APIs are very well built, and it will really help you understand or start finding applications soon enough. So if your focus is mostly going to be machine learning, then Circu is probably a good investment of time. But since we're so early, I don't think that we are still in that phase where we can choose one or the other. We have to be kind of experts in all of these, and then eventually one of them will be an outstanding winner. As of now, there is no outstanding winner, which would be the final something. But like I personally believe that there will be some sort of an OS, maybe 10 or 20 years down the line, something that I cannot imagine myself. But till that comes, we have to learn everything. So learn everything.
Another question I'd like to ask right now is more on the technical end. So this question is really related to the PMUs, which you mentioned. And this question comes from me because I recently did a project with the government of India and NREL, where we tried quantum optimization algorithms to try and find out the best, most optimized locations to where placing the PMUs fit in on the smart energy grid of India. But the question is more related to how to replace the current PMUs with some quantum sensors, and if you are doing so, what happens to the information and the the massive amount of data being generated in real time? How do you analyze that? How do you try to find some analytical benefits from the error-driven data which we are getting?
Yes, that's a great question, and the short answer is, it will require tremendous amount of research funding to answer your questions. So, because we don't know until we have done that. But my initial understanding is that once you have these quantum-based sensors, denoising the data will be a research domain in itself on how we develop new kinds of filters. Because even for PMU data today, you have lots of noise, you have lots of bad data. So for that, scientists have developed some, ensemble method of filtering out the bad data, or doing an event detection based on that PMU data. But now once you have quantum sensors, you will have a whole different level of complexity in understanding say what is a bad data or good data, what is an event in the power grid, what is not an event on that power grid. So probably new kind of filters. Some filters can be hardware based and co-located with the quantum sensor themselves. That might be required, and it will only be possible through research. But my initial direction, if we had to write like a proposal together or idea together, I'd say that we need these kind of quantum sensors along with co-located hardware filters, and on top of that, map it to some existing, like a classical AI ML algorithm for event detection that people have already developed. So that would take care of the data processing part, because the classical computers are good at these kind of data processing, but the sensing and the filtering can be better handled by a quantum. So that way, by having a good balance of what job we assign to the quantum side of things and what job we assign to the ML or the classical part of things will also be required for more wider and near-term deployment of quantum sensing technologies.
Thank you, Sayon. Ron from Chicago asks, can you envision a future quantum DSL and what capabilities would you like it to have? And Ron is interested in a quantum compiler project, he says.
Well, by DSL, you mean like a modem DSL or?
I think so.
Okay, so I don't know. I don't know, Ron. I mean, that's a great question. Quantum DSL, I never thought of that. I mean, quantum computers probably require like very different temperatures to work on, but I don't imagine a quantum computer kind of sitting on my desk.
Oh, okay. Ron actually means a domain-specific language. This was a domain-specific language you use yourself, Ron. Thank you for elucidating.
Okay,
yeah.
thank you. I was thinking like I was thinking like a DSL modem or something.
Right. Also my first thought. Yeah. So
a
a quantum domain-specific language.
Absolutely, absolutely. It will be required. I mean, just like you know, like designers use Adobe Photoshop, while a power systems engineer would probably use something like a MATLAB or PACC. But at the end of the day, they're all solving, you know, like large linear algebra matrices. They're all inverting matrices, right? But the tools of the trade are completely different. So similarly for quantum, even in quantum, you'll be taking large matrices, inverting them, flipping them, finding their eigenstates, the same operations. But all these tools will need to adapt to what a human being actually wants. So if I'm a designer working on quantum computing to generate art, my tools will have to be different, or how I communicate with a quantum computer needs to be absolutely different from, say, a person trying to install PMUs and trying to do the filtering. So, but again, the question is a domain-specific language. There is another parallel thing that I'd like to highlight is, you know, the whole notion of UI and UX and how people work with computers is changing in the era of artificial intelligence, right? So you see, like with ChatGPT, you don't even need to, and especially with the code interpreter plugin, you don't even need to write code. You just need to type something and it generates the dashboards for you. So probably in the future, people will not need any more dashboards or standalone software. People can just spin up a software just when they need it and dispose it when they don't need it anymore. So whether this movement due to generative AI is going to have an impact on how programming languages are developed is a factor to seriously consider, because maybe in the near future, by the time quantum computers are ready for prime time, the whole field of UI and UX may have evolved so much that there may not be need for a domain-specific language at all. But let's assume that quantum computer, that UI UX would still be the same, and there would be an operating system with different software. And of course, my perception is that there is going to be domain-specific language for anyone trying to use a quantum computer for something. There cannot be a universal language. But at the same time, the evolution will be similar. There might be some sort of, like how IBM Qiskit is there. There will be some high-level abstractions for some low-level tasks, but how people use that will be very defined by the profession that person is in.
Perfect. Would like to wrap up with a personal question asked by Durjesh, namely, what motivated you to enter the energy sector?
Oh, that's a great question. My motivation, honestly, I grew up in India, and in India, your motivation doesn't matter much when you're choosing your line of study, because You go through an examination, and depending on how much score you get in that examination or rank you get in that examination, that determines your college major, right? So my life was preset based on that examination I took, and I got into an electrical engineering program. Now it was for me to love electrical engineering, and that's how I kept continuing on electrical energy system rather than branch out to an MBA or a MFA degree or something like that. So the question, I like to rephrase your question, is what kept you in the energy system, not what you got you into energy system. So what kept me in energy system is because, you know, I grew up in a part of India where power outages were extremely common, and it affected our family's livelihood. It affected our family's comfort, and I always believed that reliable and resilient energy systems are a fundamental human right, because dignity is a fundamental human right, and uh, and energy plays a big role in human dignity, and that somehow stuck with me. And I believe that if I continue to be in these energy systems, I'll live long enough in this sector to make at least a small contribution in making the power grid a little bit more uh, reliable, resilient, so that if there is a storm or if there is these frequent heat waves, uh, the powers, you wouldn't even notice a blip in the power systems. No one faces a power outage. Nobody is suffering because there is no water in their homes, or suffering because their ventilator is not working and people are on life support. Those are the kind of things that help me stay motivated in this energy systems and stay within this domain.
Amazing. Thank you for sharing that. And I guess there is actually one more really good question to ask as the very final question. Dunya asks, do you think that quantum could be useful for predictions and planning in the climate and energy sector, or is it more about minimizing and dealing with the consequences?
The former, great question. It is going to be used for planning in my understanding of how things are shaping up, because the number of scenarios, say for example, say new materials can be discovered using quantum computer, and that has been discussed in several papers. I have not validated, but I trust those amazing papers that come out on Nature and other, that you can design a new material using quantum computer. So that is kind of a planning exercise where you can design a better tire for a road, which for say, and imagine a future where, you know, the Earth's temperature has increased by 3 degrees Celsius, and there is heat waves during the entire summer, and you're driving through Route 66 in Arizona, and the asphalt is melting, right? And then for those kind of natural rubbers do not exist like that. So people have to imagine that kind of a scenario, and using quantum computers, they'll be able to design a rubber for those kind of tires that will work on those kind of circumstances. And it can help you prepare for many of those doomsday climate change scenarios that people are thinking about together. So I personally believe that, you know, at one point, you know, like when a climate crisis is kind of pushing a segment of society into like despair and disbelief and doomsday kind of gloom, quantum computing is a really big hope for society, where they can come up with new things that is not typically found in nature, new drug discoveries, creating resilient power systems by preventing blackouts that is possible as more and more heat waves come up or storms increase and cut down segments of the grid. So it is a big hope, and you can use quantum computing for forecasting these scenarios, optimizing by having a lot more inputs, and designing stuff that doesn't exist. So quantum computing coupled with the power of generative AI and the future of interfaces, it gives us more hope for the future than some other bad news that you might be reading on the press. So a lot to be excited about in it.
Very excited. Sayon, thank you for this great and inspiring talk. It was really great that you joined us, and there will be many take-home messages today. WOMANIUM always looks into the future. What are the topics that will be big in 10 to 15 years or even beyond? And people should know about right now. People should be trained in right now. And energy has always been one of those from the start. WOMANIUM started with a project and training program with ARPA-E, ARPA of Energy, part of Department of Energy in the US, including projects with NREL, where Sayonsom Chanda is at. Working with the Naval Nuclear Lab, working on quantum sensing projects with the Naval Nuclear Lab and also with NETL, the National Energy Technology Laboratory. Thank you for sharing all this, the insights of quantum into the energy space and even beyond. And we look forward to collaborating more, and this is only the start.
Thank you so much. I appreciate you having me.